Okay, so today we're finally going to get into linear regression. Before that, again, your blog should be done by next week. I would say that's a good time. This week is probably a good time to get started on the blog, especially because with this week's material, you can start getting familiar with like what you're going to be doing for the project. So I think best to get that blog out of the way before the real work begins. So remember that. Okay. So to start, linear regression is a model, and we're going to be talking about this one model for the rest of the phase. Next phase, we're going to be talking about a lot of other different models. So just to like show you all the scope of things and what things are going to look like, that's kind of the structure. Linear regression for the rest of the phase. Next phase will be a bunch of different models. So it'll almost be like one new model per study group, which is going to be intense, but linear regression is the one that we probably go into the most depth with, just because it's one of the most commonly used ones. So before talking about the model, we talk about statistical learning theory. And the whole idea behind statistical learning theory is constructing a model to draw certain conclusions from the data. And we'll look at an example later on and see what kind of conclusions we can draw from it. And then after drawing conclusions from the data, use this model to make future predictions. So it's kind of twofold. You can model to infer patterns or relationships within your data set, but also you can use the same model to make predictions. It's kind of twofold. As a quick tangent to talk about some terminology, you might have heard the phrase training a model, and also the words model and algorithm, which sound like they can kind of be the same thing, but more specifically, a model trains via its algorithm. So you can think of an algorithm as a series of steps that a model takes to train. In this case, linear regression uses gradient descent as one of its methods to train the model. So gradient descent is one of the algorithms in which linear regression can train its model. Linear regression can train. We'll get more into gradient descent at the start of next phase. And so the math of gradient descent is not very pertinent to this phase. So while the best model for your data is a regression that has this form, and we'll talk about what this is a little bit, where Y is your predictive value, X's are your variables, and betas are your parameters. The algorithm is just the process of choosing the right values for your parameters. So we'll talk about, I'll come back to this in a little bit once we get into what a regression is. Okay, so that was a quick terminology aside. Next, we're going to talk about our data. So in the context of statistical learning, there's two main types of data. There is our dependent variables and independent variables. So dependent variables are data that can be controlled. Other words for it, outcome variables, target variables, response variables. And then you have your independent variables, data that cannot be controlled, which are your predictor, inputs, explanatory variables, or features. So in models, and especially in this model that we're going to be working with for the next couple of weeks, the independent variables are the variables that will affect the dependent variables. So that direction of causality is kind of important to know. Your independent variables affect your dependent variables. Graphically, conventionally, the independent variables on the x-axis or the horizontal, and the dependent on the y-axis. So in this example, we have some data on people's ages and their income. So in this case, you can see that age is the dependent variable, therefore, sorry, age is the independent variable, therefore it's on the x-axis, and we're trying to predict income. We're trying to see if age has some effect on annual income. So you want to see, given the person's age, what income would they have, or what income would we predict them to have? If for some reason the question was like, okay, based on your income, can I predict your age? Then it would be the other way around. So important to think about the direction of causality. Sometimes, like in this case, you might have situations where you want to use age to predict income. You might have situations where you want to use income to predict age. Sometimes it doesn't make sense. Like sometimes you're not able to flip those causalities around. So that's something to think about when you're dealing with your own independent and dependent variables. All right, so now to finally talk about linear regression. So a statistical model will basically define a relationship between a dependent and an independent variable. This statistical model of a linear regression defines a linear relationship between age and annual income, meaning that the relationship can be described with a straight line. So therefore, we can see here the relationship between age and income can be showed using a straight line connecting all the individual observations in the data. So this line here is our fit model. So as I was saying, linear regression is a type of model, but this particular line is a fit model because given a linear regression, you can basically adjust, and I think I talked about this briefly last time, but with this data, it's hard to say, right? Like, is this the best line? Is this the best line? Is this the best line? All of these lines are linear regression models, but this black line is the fit linear regression model. And we'll see that in the code in a little bit as well. So this straight line going through our data is our linear regression model, our fit linear regression model. So any linear regression model follows this format. If you remember from math, when you had like the equation of a line, y equals to mx plus b, I think is how most people learned it. This is actually exactly the same thing. Y equals to beta 0, which is the y-intercept or the plus b part that we used to have, plus beta 1 times x, and beta 1 would just be the m. So beta 1 is sort of like this, beta 1 is the slope, and beta 0 is the intercept. So interchangeable with our y equals to mx plus b. In statistical learning, we just use betas instead. So here we have our dependent variable y, our independent variable x, and then our two betas are our parameters or our coefficients. So therefore, training a model is the process of figuring out what the best parameters or coefficients are when you're constrained by a model. Any question? I know there's a lot of terminology there, but any questions to clarify? All right, cool. Okay, so now that we know that any straight line going through your data is a linear regression model, and the process in which machine learning is occurring, or the training a model, occurs when you're trying to figure out what the best y-intercepts and the best slope are. All right, so how does one choose this best fitting line? We'll talk about this in more depth at the start of next phase, but every model has an associated cost function. And I say here, every model has an associated cost function that its algorithm uses to learn the best parameters. Now, in this case of a linear regression, the cost function is actually a squared error. So what does squared error mean? Let's say we have this line here, and we have all of these data points. The squared error, we're actually going to take the distance between each data point and each line and square it and sum it together, and that will be our overall squared error. So what does that mean? Every data point, let me clear this, every data point has an actual value and a predicted value. So let's just take a look at this guy over here, this point that's out here. Its actual value is around like what, 37, let's just say 37,000. Now its predicted value, you would actually have to trace up to this line. Its predicted value is actually 50,000. So you have this error of about 12, 13,000. And then squared error, you just have to take the square of that. And then you're gonna do the same thing for all of these data points, sum it together, and that's your sum squared error. And that is kind of the cost function that linear regression uses. So down to here, least squared error, basically a little bit of background on least squared error. You might come across a bunch of different methods used to solve for linear regression. We're going to go through these at the start of the next phase. Matrix multiplication, gradient descent, covariances as well. I think in your labs, they go over like the covariance method of solving linear regression, which is, you'll see it's good to know, but you'll never have to do that calculation. But the similar thing that goes through all of them is all of those methods will minimize the least squared error. And what I mean by minimize least squared error, with this best fitting line, we have a least squared error of, let's say, I don't know, 10,000 is our least squared average error. If I had this other line that looks like it could roughly also fit, like see this green line, looks like it could also be a good fitting line. If we take the least squared error for this green line and all the data points, it would be higher than the black line because it decided that the black line had the best fit. So this best fit line is the one that has the smallest least squared error for all the data points. So that's how it decides on what the best line is, up, down, or tilt, left, right. Okay. All right, so next. So as I mentioned, every model has an associated cost function that its algorithm uses to learn the best parameters. This is kind of the diagram I was drawing earlier. And in mathematical terms, this is how you would write it out. So into terminology, because you might see a lot of these y values all over the place, and it is kind of confusing to keep track of. Anytime you have just like a regular yi just means for like every single data point. The I would say not super important, but every time you see a regular y, it is the actual value. So the observed result. Every time you see like a little hat on top of the y, like this here, you actually call it y hat. This comes from the model. So usually you read these values off of the line and these values off of the data point. And so why this is the same as the sum of square residuals is this is the difference between the value of the actual observed result and the predictive value squared. So that's your squared error. Another word for error is residuals, which is why it says residuals here. So you're just squaring all of these red line distances, squaring them, summing them together. Questions about that? Okay, so that's how you figure out what is the best fitting line. There's another metric that tells us how well fit our best fit line is, and that is the R squared. So a metric to determine how well the line fits our data is the coefficient of determination, or R squared. Now, R squared has a formula, which we'll get into a little bit, but the whole idea of R squared, it is comparing how well is this line fitting in comparison to the worst line. So there's a couple of different things going on here. As you can see, they're using this data point as an example. So with this data point as an example, first you measure the residual that we had over here. So you can see that this red arrow here is a residual. And another distance that you're going to take into consideration is y hat. So this orange line over here, sorry, not y hat. This orange line here is called y bar. This orange line is just the average y of all of your data points. The logic behind that is, let's say you don't know anything about modeling. You don't know anything about building a model. The best way to make some sort of model or prediction is just guess the average, right? Just guess the average. And so that's what this y bar is. I'm going to scroll down in a little bit, but basically you have to keep track of the distance from the data point to the model and the distance from the data point to the average. And it's actually going to take that proportion. So if I scroll down to this over here, you'll see that there are those two proportions at play. So first we have over here, you can see that we have the residual that we were looking at earlier. We have the actual value minus the model value of y hat squared. And then here we have the actual value again. And instead here, we're minusing the average y. So y bar, anything with a bar on top of it, is average. So that's the formula for R squared. And that's kind of like what it's doing there. It's comparing proportional or in relation to the worst model you could do, which is just a straight across line. How well does the line fit the data? There's a bit of reading here. And I know that there are some labs that have you actually write this formula out, which could be good practice. But I'll show you in a little bit how you actually don't have to do that whenever you're doing data science modeling work. One last thing about R squared is, how do you interpret R squared? So let's say you get an R squared value of 0.85, how you should describe and how you should interpret. And actually in your project, whenever you run a regression and you get an R squared value, I do want to see this interpretation. If you get an R squared value of 0.85, you should describe it conceptually as 85% of the variations in the dependent variable y are explained by the independent variable in our model. So in a little bit, we're actually going to run through an example right after this, and we're going to interpret it this way. So I know we've talked about a lot of concepts so far. Any questions on that before we get into actually doing our first regression?
Sorry, you mentioned you want to see this in our labs or just
I
like
want to see this in your project.
projects. Okay, got it.
Yeah. In your projects, whenever you get an R-squared value, or at least when you're evaluating or interpreting your model, this should be the interpretation. Because I've seen a lot of like incorrect interpretations, like, oh, this model is performing at 85%, or yeah, this model is 85% accurate, which is actually not a correct interpretation of R-squared. So whenever you're interpreting R-squared, this should be your interpretation. Okay, so let's take a look at our first regression. We're going to be using all our same libraries. The new ones that we're going to talk about are stats models, which might look familiar because we did talk about this when we were doing our ANOVA last week. But here we're importing our pandas, matplotlib, we'll see why. So this is going to be our data to start. In this, we're going to try and predict weight using height. Of course, you can always flip it the other way around, but in this case, we're going to predict weight using height. We'll look at this later. We can sort of quickly do a very, very quick EDA to just see like what the weights are distributed like. This is weight. This is height. You can see not a particular, there's only 20 data points, so there's not like a very meaningful distribution you can get from that, but always good to do EDA. But let's take a look at the scatter plot. So based on this scatter plot, you can see, okay, yeah, it looks like we can pretty much fit like a solid line through this data. So let's do that. What I'm going to do is set up this with stats models, and I'll walk through what each of these lines are. So first we have the formula F. F is presented as a string. And the reason for that is, I mentioned this last time, but this is basically the syntax for the programming language R, and stats models is adapted from R. So therefore we have to use this syntax. So its weight is you're going to predict weight using height, and using would be that little squiggly line tilde. If you have more variables, which we're actually going to talk about tomorrow, let's say you have age as well, you actually just do plus age plus, I don't know, I can't think of anything else, but yeah, if you have more variables, you just put a plus there. So weight and height, that's our formula. Next, you see that we actually imported OLS directly. So OLS is our ordinary least squares, which is the algorithm that we're going to use to solve our linear regression from stats models. So here we have formula equals to F and data equals to data frame. So OLS takes in the formula and also takes in the data frame, and these just have to match the column names. And then at the end of this, we're just stacking a method .fit. Now this .fit is literally the code that fits the best line to the data. So this .fit is literally doing all the calculations to figure out what is the best slope and intercept for this straight line. And then you are actually going to print out a summary table, therefore model.summary. So let's run this. And just like that, we have a model summary. So first thing that we see here, oh, actually, this is too small now. All right. So first thing that we see here, the dependent variable is weight. The model is OLS, and we're using the least squares method. Usually, pretty much 100% of the time, that is what you're going to see. You should not see anything that you don't expect there. If you do, let me know. You also see when it's run. You have 20 observations here. DF residuals, degrees of freedom of your residuals. Basically, it's saying that because we're predicting two things, or we're trying to find the best parameter values for two things, our intercept and our slope. That's why it's 20 minus 2, which is 18. We have our R squared, adjusted R squared I'll talk about tomorrow, but we have our R squared. So our R squared of 95.5% is literally saying that we can explain 95.5% of the variance in our weight based on height. That's how you would interpret that. I know it's something to get used to because it doesn't really, I don't know, I feel like it took me a while before that sentence actually made sense. But yeah, adjusted R squared we'll talk about tomorrow more, but basically adjusted R squared takes into account the fact that when you have more and more independent variables, adjusted R squared will change, and adjusted R squared is always a little bit lower. I've copied and pasted this from one of your labs, but if you ever wanted to know what each and every one of those things mean, quick explanation over here. But we actually don't need to use all of this information. For our purposes, we're going to take a look at R squared. R squared is going to be important. Coefficient is going to be important, and the p-value is going to be important as well. So we're going to go through these things one by one. So first of all, coefficient. Coefficient is just our beta values that we were trying to figure out the best values for. So first, this coefficient, intercept coefficient of negative 204 is saying that our y-intercept is just negative 204. And then our coefficient of 5.539 for height is just saying that with every increase in 1 unit of height, so 1 unit of height increase will cause a 5.539 increase in weight. So this is just saying that with every, I think this is in inches, in every inch of height that you have, your weight will go up by 5.539 based on this data. That's how you interpret a coefficient, which is actually the relationship that we've learned from this model and from this data, right? At the start, we talked about, we can use statistical learning for learning about our data as well as predicting. So in this case, we've learned that the relationship between height and weight is an increase in 1 inch of height will lead to 5.539 increase in weight. If it's negative, the change in weight will be negative as well. That's coefficient, and coefficient analysis is actually pretty important. It's actually something that's used very, very much when you're using models for research or for learning about your data. All right, so the next thing that we have to look at is p-value. Now here you can see that p-values are 0, which if you remember the things I was saying over the past few weeks, low p-value is a good thing. And right after this, I'm gonna explain what this p-value is all about and where it comes from and why, and what is the hypothesis or the test that's being done here. Questions about any of this stuff so far? All right. So yeah, pretty neat. We just had those like couple lines of code and the regression was done for us. We did not need to by hand calculate R squared. We did not need to calculate anything else. All we had to do is just make sure our data was in a clean numerical way. And we can gather all of this information from this summary table, which is a lot of what a data scientist's job is, just interpreting outputs such as this. All right, so I have the description here. It's also in one of your labs. I'm not going to go through all of it here. Okay, so hypothesis testing and regression. This is related to that p-value of 0 that we saw earlier. So the hypothesis setup is with which, if you remember, that's one of the first things that you always have to do prior to doing any statistical test. The hypotheses are, null hypothesis is that there is no relationship between the dependent variable and the independent variable and the dependent variable, basically no relationship. Alternative hypothesis is saying that there is some relationship between the independent variable and the dependent variable. So what does no relationship mean? The fact that we can say here that this coefficient means that, okay, height goes up by 1, weight goes up by 5.539. That is a relationship. The fact that a change in height affects a change in weight. So as long as there is a number here, there is a relationship. And as long as that p-value is low, below 0.05. So no relationship, what does that mean? No relationship means a coefficient of 0 and absolutely 0. Because a relationship of 0, a coefficient of 0 means that no matter how you change your height, weight doesn't change. That means that weight is not affected by height at all. That's no relationship. And it has to be exactly 0 to have no relationship. Question about that?
How often will we see a coefficient close to 0 when running these analysis?
Very often, actually. I mean, depending on the scale of your data, but it's not rare to see a coefficient that's close to 0. But the fact that it's close to 0 and not exactly 0 means something. The fact, like, if you have a coefficient of like 0.001, that is still a relationship. versus 0, because let's say that we're talking about something different. Let's say it's not weight, but let's say it's I don't know, height affects, oh my gosh, I can't think of a good example, but let's just say height affects what's a small number? Let's say height and the effect of, oh,
Hair
your
length or
weight.
something?
Yeah, hair length or something. Yeah, that's okay. Let's do that. And hair length measured in like meters, because I know hair is like not in the meters amount. But yeah, if you have a coefficient of 0.001, if you increase your height by 1 inch, your hair length increases by 0.001. And that is still a relationship. The important distinction here is, let's say I had a coefficient, and doesn't matter what number that coefficient is. If I had a high p-value, now that just says that that relationship, no matter what the number is, non-zero number, is not significant. So instead of seeing 0 values in your coefficient, and I mean absolutely 0 values in your coefficient, very likely you are more likely to see some random value of coefficient and a high p-value versus 0 for coefficient, 0 for p-value. I hope that it's kind of abstract to think about. I have more to say about that, but does anyone want to clarify anything based on what I just said?
I got it. Thank you.
Okay.
So I had a couple of questions. Is R square or coefficient, are they mutually exclusive, or are they, do they have a relationship, some type of, or is that part of the hypothesis testing that you're doing, is to see the relationship? Or
all right, so the hypothesis testing is solely just testing whether the coefficient is significant or not. And I'll get more into that hypothesis later on. R squared, they're not directly related. R squared and these coefficients and p-values, they're not directly related, but they come from the same algorithm. So therefore they're related, but they don't affect each other. It's not like if you have like high or low coefficients, your R squared goes up or down.
Oh, okay. All right. Thank you.
Yeah, they're calculated from different parts of your result.
All right. Thank you.
So, okay, sorry. So my question is it possible to have then like a R squared that's close to 1 or -1, but then also have like a p-value that is actually above your hypothesis of like 0.05?
Absolutely, it is possible. We'll actually see examples of that tomorrow when we talk about multiple linear regression, because today we're only doing regression with one feature predicting one target. Tomorrow we're going to talk about multiple features predicting one target, and we'll actually see an example where you'll have insignificant p-values or statistically not significant p-values and fairly high R squared as well. And something I forgot to mention, R squared is measured between -1 and 1. Yeah. But yeah, all good questions so far. Okay, but more about this hypothesis. The null hypothesis is there is no relationship, and alternate hypothesis that there is some relationship. So what this p-value is saying is that what we're testing for is that, let's say we have this coefficient value of 5.539. This coefficient value comes about by fitting our line that reduces the amount of least squared error. That's where these coefficients come from. However, we want to test whether this coefficient is observed by random chance or there is actually a relationship there. So back down to here, I think it's helpful to think about, if we have a p-value of higher than 0.05, then there is no significant relationship between dependent and independent variable. And that our slope parameter of m in this mx plus c, or this value here, is not significantly different from 0. So that's what we're testing here. is this coefficient statistically significantly different than having a value of 0? And that's where this t statistic comes from. That's where the standard error comes from, is where these p-values come from, is where these 95% confidence intervals also come from. And that's from doing the test of, is this statistically different from 0? And we want it to be statistically different from 0. Questions about that? I know it's kind of abstract, and I will admit that when I was learning this, I had no idea what any of that meant, and I still got through. And like, you can still get by, not fully understanding. Just know that if there's anything you want to take away, and if you're feeling very, very overwhelmed by the statistics, just say that low p-values is good. And also in how you interpret these coefficients, the fact that if you have increase 1 of height will give you a 5.539 increase in weight. And the intercept, usually data scientists don't really interpret the intercept that much, but intercept will also be like, all right, if we set height to 0, weight will be -204. And you can see why with that interpretation, data scientists don't use it so much, because they don't really care about height equal to 0. They just care about like, okay, changes in height lead to what changes in weight. All right. Questions before we move on to the next section. I will say that this will make, at least in my experience and in like how I see like other students work through this material, this makes sense with practice, and the more that you see it, it'll get easier to interpret. Okay, I know there's a lot of words here, and this is just more of a review on p-value, which we talked about last time already. Okay, so next, I want to talk about some assumptions for linear regression. If you've already started looking at your data set, this is where you can start doing some EDA work. So regression is a parametric technique, which means that it uses parameters learned from the data. In this case, our parameters were these coefficient values of intercept and slope. And these were learned from our data. Right down here. Because of that, certain assumptions must be made. And these assumptions define the scope of regression analysis. And it is mandatory that the underlying data fulfills these assumptions. If it's violated, the regression will make biased and unreliable predictions. So luckily, we have measures to check for these assumptions. I will say that for these assumptions, it does say mandatory that these the data fulfills these assumptions, but there are no like set thresholds. And you'll see as I talk about these assumptions, a lot of it is just based on eyeballing your EDA. And so that's something you can actually start doing now if you would like. So the first assumption for linear regression is linearity. And the assumption states that there is a linear relationship between the response variable y and the predictor x. So linear just means that the change in y by a 1 unit change in x is constant. Now, these two are linear relationships. You can see the positive slope here, negative slope here. And this is just a non-linear relationship. Again, the way that you look at this, you will probably just plot some scatter plots to see if there is a linear relationship or not. Usually the threshold is not very high for this linearity, but you can sort of assume that if your data is linear between your x values and your y values, you will probably get a more reliable model, right? Because it says here that if these assumptions are violated, the regression will make biased and unreliable predictions. So just as a quick example, let's just imagine that, okay, let's use this nonlinear one as an example. And we're going to do something really extreme. Let's just say that our data points look like this on this super curvy line. And we decide to fit a linear regression through it anyways. A linear regression is going to coerce itself to fit that data. And it's going to coerce itself in and maybe look like this green line over here. Let me make it a little thicker. All right, let's just say it coerces this thick green line to be our model. As you can see, the R squared is probably not going to be very high because you have high residuals. Like you're going to have high errors, especially for like these points over here, they're down here, maybe these points up here, these points here. So it's not going to be very reliable. And if you have linearity, if you have something that looks more like these two other graphs over here, you're just going to get more reliable predictions. We're going to talk about some methods tomorrow on how you can force your data to have a little bit more of a linear relationship. So it's not the end all be all if your data currently is not linearly related with each other. So basically for your target variable and any of your features that you're using, you just want to check that they are linearly related to each other. What if you have non-numerical values? What if you have like categorical values? You'll talk about that tomorrow. So for this assumption, you can usually check just with scatter plots. At this stage, you can also check for outliers. So here you can see that there is a fairly straight line and you have one single outlier on the top. And that's something that you can also see from the same scatter plot. Outliers will definitely affect your model. In this case, you can see whereas this orange line should have been straight through all of these points down here, this one outlier managed to pull it a little bit upwards. And so this did end up biasing the model. I will say that how you decide to remove outliers is very, very subjective and it's up to you. And things to think about are like, okay, in context, what is it to be an outlier? So for example, in our provided dataset project, we're predicting the price of houses, right? Now these houses, and I know from the dataset, it's a pretty wide range. I think you have like houses in like the $30,000 range, going all the way to like $7 million, I think. It's like a pretty wide range of housing prices because you have all the regular homes and you have super luxury homes. And those, a lot of people will call outliers. But think about it in context and think about what you want to use your model for. If you want to use your model to predict for all prices throughout the entire county, then why would you want to discard these luxury homes? Because if you want to use this model to predict for luxury homes, you will have your line that is fitted to your other data. Actually, let me draw it out so it'll be easier to see. So let's just say we have all of our regular houses here, and we have some luxury homes all the way up here. If we fit our line with the luxury homes, our line will look a little bit more like this green line. And if we don't, our line will look more like this. So if we fit this green line, we'll be able to use our model to predict for the entire range of homes, which could be what you want, could not be. It really depends on your context. But we are sacrificing a little bit of accuracy. We're going to sacrifice some R squared. We're going to sacrifice the predictions because look, these predictions are going to be pretty off. Yeah. Now, alternatively, you can say, all right, let me just create this linear model to only predict non-luxury homes. Then in that case, you can have a better R squared, but you just have to remember that you cannot use this model for a luxury home. So there's a lot of thinking that is involved. And I know that we're talking about a lot of things all at once today, but when we get to the project, I'm gonna want you all to think about that as well. Questions?
Quick question. I was just thinking, if you have, I forgot the name of the statistic, but you know how you can determine a number of variables to use in like, I guess in an analysis, would this be like an appropriate use? Let's say you had like enough variables to do, could you do like two separate analyses, just one of low income and one of high income?
That's a good question. So that would be like, actually you can use like an ANOVA for that to determine whether there is like, is there a significant difference in the prices between, you first have to set your own threshold first. So you would say, okay, above $1 million is gonna be luxury, below $1 million is not luxury. And then you would do some sort of like ANOVA test or t-test to figure out whether, okay, should they be using different models? Now that is something that you can definitely do. You can say, all right, for non-luxury homes, I'm going to have this orange line here. And for luxury homes, I'm going to have like this separate red line over here. That's actually something that is done. For this project, I only want you all to build one model because you'll see tomorrow that the process of doing one single model is quite involved. So if for this project you decide, okay, I don't want to do luxury homes, your model will only be for that like smaller subset of non-luxury homes, and that's okay for this project. Awesome. But yeah, this is actually very commonly seen. So let's say if you think that there are like 5 different tiers of houses, you will build 5 different models, and the coefficients for all of them are going to be different. So that's definitely a possibility, but don't build 5 models for this project. We don't need to do that. Okay. So that's the first assumption, linearity. And also I just want, again, this is something that you can probably start doing now because it's part of your EDA, but also just think critically and think in context about your outliers. And what does an outlier mean? If you take out certain data points, is that going to affect how you can use your predictions or how you can use your model? All right. So there's going to be 3 assumptions that we're talking about today. The second one is normality. So this assumption says that model residuals should follow a normal distribution. So take note, I did not say that the variables need to be normally distributed. So remember when we looked at our plots here, this is definitely not normally distributed. I think our weight one was also a little better. There's only 20 data points here, so it's hard to see, but the variables do not have to be normally distributed. I think that's a misconception that people have. The residuals have to be normally distributed. And this assumption is something that you can only test after you fit your model. So after you fit your model, you have to check on the residuals. Now, what does residual mean? Residual is basically that difference between the data point and the line itself. And so you will get that information. I'll show you via code how to do it easily. You'll get that information and you'll just plot it on a histogram. So you can see here, residuals should be centered around 0 because you should want like an equal number of positive and negative residuals at the same time. So this is a good thing. This is not good. You can see here that 0 is all the way on the left here. There's a skew. And this is just saying that there's a lot of outliers on the high end that your model is failing to predict. So a couple ways that you can look at this. One, through this residual histogram. 2, through a QQ plot. And the QQ plot is actually quite similar to what we were talking about before with the Kolmogorov-Smirnov test, where it compares the residuals to a normal distribution. There's a lot of ways that you can interpret a QQ plot. I've actually linked something here to explain different QQ plots and how you can interpret them. But basically what you want to see from a QQ plot is that the points are nicely lined on the diagonal. They're aligned with the red diagonal here. Code for that, we're going to be using SciPy. SciPy has that as well. You can first grab the residuals from your model. So this model.resid model was the model that we fit earlier from all the way up here. Let me bring back my table of contents. So our model is what we fit from here. Let me just resize this real quick. Models from here. We got our residuals from here, and actually by output residuals, it is basically an array of like how off each point was from the line. And then we can do this as a QQ plot. Feed in the residuals. The distribution that you want to compare it to is the normal distribution. We have this 45-degree line, and then this is our QQ plot. Basically, this is just showing us how it is distributed. If it's along the line, it's normally distributed. If it's off of the edges, it means it's either, I forget which way it is, but it's either too flat or too peaked. So, but there's an article here that just walks through different QQ plots and how to interpret them. So this, how you would interpret, if you see something like that, how do you interpret it? If you see it like that, how do you interpret that? So I honestly, whenever I have to interpret a QQ plot, I like to pull something up because I always forget what each shape looks like and what that means. All right, so that's residuals being normally distributed. All right, so the last assumption that we're going to do is also another one that you can only test for after fitting your model. It is the homoscedasticity test. And homoscedasticity basically means equal variance. That's what homoscedasticity means. Heteroscedasticity means that basically means unequal variance. So heteroscedasticity, which is very hard to say, refers to the circumstance in which the dependent variable is unequal across the range of values of the predictors. We'll see more examples of all of these assumptions tomorrow and next week as well. But when there's heteroscedasticity in the data, a scatter plot of these variables will create a cone-like shape. And what we look for in terms of heteroscedasticity or homoscedasticity is we actually look at the residual plot. This is just an example of showing what hetero versus homoscedastic means. And it's about the variance. So across the range of a variable, how varied are your data points? So if you imagine like, okay, let's say that this is, let me just write it out. Let's say that this value over here is our height. And let's just say that this is weight. A heteroscedastic plot is saying that for lower values of height, weight varies less than at higher values of height. That's heteroscedastic. What we want is homoscedasticity, where it's equal variance throughout. Now, this is also, even though I just said weight and height here, this is more in the context of your residuals as well. So what does that mean? Here, this is the code for it. I'm going to show you all the code for it first. This is something that you can plot. Regression exogenous, which is something that you can plot as well. But first, I want to talk about this, because this is what we use for looking at heteroscedasticity. So this plots our residuals with respect to height. So what that means is across different values of height, these are our residuals. So it looks like that for heights between 58 and 62, and let me see if I can zoom in better on that specific, this is, okay. So on this specific graph here, heights between 58 and 62, the residual is positive, meaning that we tend to be over predicting our weight at lower values of height. So because a lot of these residuals are in the positive end, we're over predicting our height. Now between 64 and 70, it looks like we're under predicting our height a lot more. And then on this higher range, we're over predicting again. Yes, we only have 20 data points here, so it's fairly volatile. But the idea here is that if we're using this model, we would have to say, okay, for different ranges of heights and weights as well, we have different levels of reliability when it comes to how well our model predicts. Because based on our data, it seems that, okay, within the ranges of 64 and 70, they're always under predicting weight. And within these other ranges of like outside of that zone, they're over predicting weight. And so ideally what we have is actually something that's a little bit more uniformly distributed. Like we want to see something that looks more like this, such that across the entire range of height, we have fairly similar reliability of our model. So you can sort of think of that as like it's consistent. It's fairly consistent throughout the different ranges of height. So that's the hetero/homoscedasticity assumption. And again, this is also something that you can only look at after you finish modeling. So let's say you run a model, great R squared, low p values, awesome. But then you take a look at your this residual plot, it looks like this. You're like, ooh, okay, even though my R squared was good, my coefficients and p values were good, my residual is not good. So that means, and actually something that's fairly common to see is a residual plot that looks like this. A cone-shaped residual plot is actually very, very common. And why that is it says that, okay, for certain values, like let's say values below 64, the model is fairly reliable, which is good, right? Our residuals are like plus minus 2.5 in this scenario. But as height goes up, our model loses reliability. The residual goes up to like plus minus 10. And so therefore we have an inconsistent model, which of course can still have a higher p-value and can still have fairly good p-values. But based on this, that's something that you have to check after the fact. It's another thing to consider when doing your modeling work. And we'll sort of talk about in context of the project next week, what to do and how you can interpret these results of your assumption checks. Cool. Any questions about that? we want homoscedasticity, not heteroscedasticity. Or if you want, you can say equal and unequal variance across a range of values. Cool. These other plots, good to know as well. So this is literally like the error. So you can see here, the fitted values are the red diamonds, and then the blue was our actual data. So you can sort of see like how off each prediction was of weight. And then these two plots down here, once we get to multiple regression, this becomes less important. So we don't actually have to talk about that. But there is some, this is also from your labs that I copied and pasted over. Cool. That's all I had to share for today. Any thoughts or questions? I would say that if you want to start working in your project, especially before we get into like the hardcore modeling stuff tomorrow and the rest of this week, I would say if you want to start getting a bit of a head start, do some EDA, do some of like the assumption checking, especially this first one. Just check for linear relationships between your target variable and all the other variables. Tomorrow I'll talk a little bit more about like what you can do if you don't have something that's linearly related. So don't feel like you cannot use your data if it's not linearly related, because I'll definitely talk about what you can do to help if you have non-linearly related data. Sweet. Final call for questions. Going once, going twice. All right, if there's nothing else, I'll talk to you all tomorrow. Same time, and any questions y'all know you can Slack me.
Thank
Right.
you very
Cool.
much.
Have a
You're
good
Bye,
night.
welcome.
Good night, y'all.
Thank
Bye,
you. Have a
team.
good night. Thank you.